Right, hi everyone. I'm Maha Agro. I'm a researcher working at MBZUAI University of Artificial Intelligence. This work was in collaboration with my supervisor, Dr. Hanan Aldarmaki, who unfortunately couldn't make it today here. So I'm going to be presenting our work handling realistic label noise in BERT text classification. Let's get started. So let me give you a quick introduction about what label noise exactly is. Label noise is errors or inconsistencies within the data labels where the given data label does not correspond to the actual label. It can arise due to cheap data annotation methods, and it can significantly degrade DNN classification performance. We know by our work that real-world data sets are full of labeling errors. In fact, a study conducted at MIT showed that some famous NLP benchmark data sets contain labeling mistakes. And this danger is even more magnified in human critical tasks such as medical diagnosis. We categorize label noise in three broad categories. The first one is randomly injected label noise. This is synthetically created label noise. Researchers use this sort of noise to study label noise. It randomly permutes labels based on a fixed noise level and a noise type. And it's independent of the data features, so it's also known as feature independent. As per recent work done by Zhu et al., they show that this type of noise does not accurately represent real-world labeling errors. The second type of noise we work with is feature-dependent label noise. This is found in data sets generated with automatic annotation methods such as distant or weak supervision. This type of noise is dependent on the input data features itself. As per the same study, Zhu et al. Show that this is more complex than randomly injected label noise. The third type of noise, we dubbed it as pseudo real-world label noise. This was recently developed by researchers at Stanford, and it mimics how humans make labeling errors. This is only applicable to data sets that contain annotations from multiple annotators. The study conducted at Stanford showed that this closely approximates real-world label noise, although it's worth noting that both of these noise types, pseudo real-world label noise and randomly injected label noise, are synthetic noise types, and only feature-dependent label noise is organic, real label noise. The researchers also showed that significant degradation in performance is observed as the noise level increases. Okay. Let me start by giving you an overview of the methods used in the literature so far. So the first category of methods is robust loss functions, which is basically taking your standard loss function and changing it so that it's less sensitive to outliers. Then we have multi-network training, which consists of a teacher and student architecture, and the teacher network feeds the student network useful instances to train on. We have robust regularization, such as early stopping or ensembling methods that prevent the model from overfitting on noisy instances. And we also have noise cleaning, which involves taking a fine-tuned models or an ensemble of models to sort samples in descending order of the loss. Here, loss is used as an error detector. Intuitively, high loss samples are usually considered noisy samples, and low loss samples are usually considered clean. So the methods I described just right now have various drawbacks. One major drawback is majority of these methods have been evaluated for image data. The study conducted by Zhu et al. Also showed that most state-of-the-art approaches that work in image data are ineffective in text classification with BERT in the presence of feature-dependent label noise. Most of these noise handling methods are only evaluated with randomly injected label noise. But feature-dependent label noise is much more complex and much more challenging. So the motivation of our work is as follows. There's insufficient research on noise robust approaches in the text classification domain, as we just saw. Most of the state-of-the-art approaches fail when the noise type is more complicated, such as feature-dependent label noise. Since, as I just described, the noising schemes are imperfect, so are the noise handling methods really robust? And as we just saw, there are new noising schemes such as pseudo real-world label noise that more closely approximate real-world labeling mistakes. In our work, we only considered feature-dependent label noise and pseudo-real-world label noise because, as we already established, randomly injected label noise does not accurately represent real labeling errors. Okay, let's get into the data sets we used. To study feature-dependent label noise, we used two African news topic data sets, Hausa and Yoruba. Both of these data sets were created using weak supervision. Both of these data sets have a clean and noisy version of each split, so we can establish a baseline. And noise in each of these data sets is fixed. To study more realistic noise, we use pseudo-real-world noising scheme. We use tweet NLP, which is a part of speech tagging dataset, and ICNLSP, which is a natural language inference dataset. Both of these datasets received additional crowdsourced evaluation, so there are annotations available from multiple annotators. We noised the datasets to 3 separate levels, 10%, 20%, 30%, to study the effect of noise at different concentrations. Here in this table, you can see the dataset statistics. You can see for Yoruba and Hausa, the noise level is fixed at 33% and 50%, whereas for tweet NLP and ICNLSP, the noise level can be changed. Okay. As I previously mentioned, BERT already conducted this sort of study for BERT with injected label noise, but they also showed that performance quickly degraded with feature-dependent label noise. And they also showed that noise handling methods do not improve BERT speech performance. Therefore, we selected BERT base as the backbone for evaluating all of our methods. We used BERT-based uncase for the English language dataset, and we used BERT-based multilingual uncase for the African language dataset. For the baseline of our work, we chose vanilla BERT with early stopping. We also adopted 2 other methods. The first one is co-teaching, which was proposed by Hanan et al. This is a multi-network training approach that consists of a teacher and a student network. The teacher network identifies clean instances for the student network. We also adopted consensus-enhanced training approach, which is also a multi-network approach which trains 2 discrepant classifiers. And the gradient updates are only based on consensus between the 2 classifiers. It should be noted that both of these methods were initially adopted for different tasks. Co-teaching was for vision tasks, and consensus-enhanced training approach was for relation extraction. But we changed both of the approaches to fit our problem setting. The evaluation metric we use in our work is test accuracy, which is formally defined as, I'm sure you all already know. Yeah. The first category of methods, let me get into the methods we use in our work. So it should be noted that we incorporate early stopping in all of the methods. First category of methods is ensembles. We hypothesize that ensembles may be disproportionately better at classification and noisy data setting. This is because noise causes individual models to learn false patterns or false correlations, but combining predictions from multiple classifiers can help filter out some of those false patterns. It can also help focus on stable patterns in the data. More specifically, we propose 3 ensembling techniques. The first one is homogeneous ensembles. This involves taking the base vanilla classifier, training it on the same data set, but each classifier is trained with different initializations and different hyperparameters. The second one is heterogeneous ensembles, which involves taking the base vanilla, which involves combining predictions from multiple classifiers. In our work, we use the base vanilla classifier, co-teaching, and theta. The third technique is boosting, which is basically taking the same vanilla classifier, but training it on different subsets of the data. We use 2 data subset sizes, which is 50% of the total data and 80% of the total data. Okay. The second technique we use is noise cleansing based on model loss. As I previously described, model loss can be used as an indicator, as an error detector. So we basically take a pre-trained language model, fine-tune on task-specific data. We then sort the trained samples in descending order of the model loss. The intuition behind this technique is that foundation model trained with early stopping should not be overfit on noisy samples. Therefore, it should be able to identify noisy samples from clean samples. High loss samples are usually considered noisy in this case, and low loss samples are usually considered clean. We only compute loss on out of sample points so that the model is not biased when making this decision. We use a fixed loss thresholding scheme, which means that if a sample exceeds a certain loss threshold, it is removed from the data set. In this way, the final data set is supposedly more cleaner. You can see this diagram with the figure, which more clearly describes the method. As you can see, we initially have the full data set. We divide the data set in K folds. Each fold has a training split and a validation split. The model is only trained on the training split part of the fold, and then it is evaluated on the validation split. The loss is used to clean the validation split, and all of the validation splits from all of the folds are in the end concatenated together so that we have out of sample predictions for the entire training data. Supposedly, the final training data is much more cleaner than what we begin with. Let me describe the results of our experiment. As I said, that we have clean version of the data sets as well as noisy versions of the data sets. So these are results for feature-dependent label noise. You can see on the top the performance of the vanilla BERT model on the clean version of the data set. And then you can see the performance of the vanilla BERT baseline on the noisy version of the data set as well. As we see, all of the methods slightly improve the performance, but performance does not significantly improve for any of them. The best performing method we found was CETA, consensus enhanced training approach. This is likely due to the fact that CETA was developed with feature-dependent label noise for feature-dependent label noise specifically. We can also see that ensembling methods to some degree produce various improvements in the classification accuracy. Here you can see the results for the pseudo real-world label noise data sets. Once again, you can see the clean data, the performance of the model on the clean data, and then the performance of the model on noisy data. You can also see that as the noise level increases, the vanilla BERT baseline performs significantly worse. Over here, we can observe that CETA does not outperform the vanilla BERT baseline. This is once again due to the fact that CETA was developed for feature-dependent label noise, but when it comes to pseudo real-world label noise, which is supposedly much more complex and much more accurately represents real-world labeling errors, it does not give us the same performance. In fact, in this case, we see that ensemble methods produce somewhat increase the peak performance, but ultimately the peak performance does not significantly increase for any of the methods. Okay. Let me discuss the results of the models a bit more. So we see the proposed methods to some extent produce gains over existing methods, but for feature-dependent label noise, we observed that CETA outperforms other methods. Ultimately, we saw that the peak performance did not significantly increase, and that the performance of ensembles depends heavily on the ensemble members. Noise cleansing with model loss does not produce consistent results. There are various limitations of our work. The first one would be that there are no experiments with other backbones. We only considered BERT-based, but other backbones such as Roberta was not considered. Deep ensembles are infeasible in practice for large data sets. For our case, the data sets we used were significantly smaller, but for larger data sets, this would become infeasible really quickly. Test accuracy can also be a poor evaluation metric in certain cases. So let me go over the future work quickly. We saw that deep ensembling techniques can outperform existing noise handling methods in the presence of realistic label noise. We experimented with foundation model noise cleansing, but Chong et al. Reported in their study that foundation model ensemble is a superior error detector. Okay, so I think that's it for me. Let me know if you guys have any questions.